Probably there is no such theorem that could even challenge Pythagorean theorem by the number of proofs. There are more than 400 proofs known so far. In this video will be shown, in our personal opinion, most illustrative and simplest of them. One big advantage is that it shows an entire process of proving step by step, and it makes this in that way that everyone can understand this concept. So, let us begin. What this theorem is even about? It basically tells that if you have the right triangle, that is, triangle with the angle of 90 degrees, or quarter of the full circle spin, then the squared area of the longest side hypotenuse is equal to the sum of square areas of two another sides, that are legs of triangle. Just a simple formula. But how to prove it and intuitively understand it? Let's imagine ourselves two equal squares with side that consists of two segments, A and B. Thus, the area of each from both squares is equal to A plus B times A plus B, or A plus B squared. But let's rearrange these A's and B's on the sides of squares in different way. On the top and bottom of left square, A and B will be in this order as shown. And on the left and right side, they will be arranged in that order. Thus, if we connect these junction points, we will get two squares. One with the area of A times A, or A squared, and another with the area of B times B, or B squared. But also, we will get two equal rectangles, each with the area of A times B. Let's mark these A's and B's on the right square, but in another order. Mark one side in a random way, but repeat that pattern sort of clockwise around the square. And also connect the junction points, thus making four right and equal triangles, because they are the parts of angles of big square, which has four right angles. Moreover, this feature is very important, because we can notice that these two sides of each triangle are legs, and each of these sides must be a hypotenuse. So knowing that, let's just mark it as C. But if you look closely, you will notice that these C hypotenuses make another square, because square has both equal sides and equal angles. And because we marked A's and B's clockwise, proportions of sides and angles will remain, and will be all equal to each other from every side. Therefore, there is another square with the area of C times C, or C squared, where C is hypotenuse of this square triangle. Look at these two big squares. They have an equal area since they both have an area of A plus B squared. But let's cut off from them pieces so that the area remains equal. That means that the pieces we cut must be equal respectively. If you look closely again, you will notice that if we divide one of the rectangles in two pieces with 1 second line, we will get two right triangles. And these triangles will be exact the same because all their sides are the same. A, B, and one side is common. But on the other hand, if you look at triangles in right square, they will be absolutely the same as these new ones in left square. Same A, B, and hypotenuse C, which is defined or some sort of log by previous two sides that are legs. It turns out one rectangle from left square can be split in two right triangles from the right square, thus allowing us to cut off same pieces from both squares. Two rectangles from the left and four right triangles from the right. As you can see, equality of areas is saved, because we just cut it off equal pieces from both squares. But look at what is left in the end. On the left side are two smaller squares left, one with the area of a squared and the second with the area of b squared. On the right side, only one is left with the area of c squared, and we know that these both sides are equal. Therefore, a squared plus b squared are equal to c squared. Quam erat demonstrandum.